Hello, good morning to everybody. It's a pleasure to launch the seminar on cold atom gases. I am the representative of the chaotic aspects. So the order are probably belong to the speakers. The Institute of Advanced Studies is mostly focused when they started. It started in 1988. We are getting out of a long military government in Brazil, and we are doing the new constitution. Consequently, the Institute was dominated by social, political, and humanistic sciences. As you see in our journal, the journal now is directed by one of the best intellectuals of the USP, scholar. We still have a dominance of social and political sciences. However, this group is one of the most important, let's say, basements for exact sciences. Also, we are evolving to promote a dialogue between the abacus and the rose, between humanistic and, let's say, natural sciences. The Institute, for those that do not know, is like a think tank. There is not a single tenure. Everybody is mobile. Everybody. So we have let's say, the benefit of movement. Is perhaps the only institute that there's something like research, a committee that indicates probably the possible directors and provost of the institute, based on the necessities for a given time. And we are very proud of our journal because now is reaching 5 million downloads per year. So it's the most read magazine in Brazil, especially for politicians. We are not having much success of their reading, so we are doing a new version to draw and paint to see if they understand. Yes, they can read, but I think the drawing aspect can facilitate the understanding. Anyways, the idea is this, to have groups, to meet people, and to promote science, to have publication of journals based on scientific journals based on complementarity. So I came here not only to greet you, the speakers, but also to thank you very much, because the necessity of this dialogue between human and natural sciences is extremely important, especially nowadays when the boundaries of knowledge. So science has to have principles as well. So information has to be, let's say, somehow infected by some degrees of principles and decisions made on other values. So I'm directing another meeting. I will step by, but I promise to stay in the last rows not to disturb the event. And thank you very much for your presence. Thank you. Easter. very much.
Okay, well, welcome all of you. I'm very happy that you made it, especially the visitors from abroad. And also, I'm very happy to see so many Brazilian scientists here to participate in this workshop. I'd like to mention that this is the 6th edition of this kind of workshop that we hold every Easter week since about 2014 or 13. And it's the topics of these workshops vary, they change. I mean, there are 3 topics which are the basis of my my thematic project, which is sponsored by FAPESP, the State Foundation for Research. There's the cold atom gases and Bose-Einstein condensation. There's the second topic is chaos, quantum chaos in particular. And the third topic, which is my specialty mostly, is the structure and reactions of exotic nuclei. This last topic, we had a workshop in 2017, and we had many people coming. And I enjoy, working in these fields. I did work in all of them. But this year, we decided to get together and discuss cold atom gases and molecular gases. So welcome again, and I'd like to call Mattias to chair the first session. Thank you very much.
All right, pleasure, yeah. So thanks very much. Also on my behalf, great workshop, great to be here back again. For me, it's like coming home. And we start right away with the first session. I think, Vanle, you're the first speaker, right? So, Vanle Bagnato from USP São Carlos.
Yeah. Thank you. Okay, well, before I start, which I need, you see, this, let me tell you that this type of workshop that's carried by the Advanced Study Institute do not supposed to be big. They supposed to be small and provoke many discussions, okay? So it's like keeping the group of people together during the week, and so this is the spirit. And the director of this institute, he wants to make sure that we talk also with other people, not in physics, which I don't think we have any in the room, right? So it's, and I will be, I will not sit, I can't give a talk on a chair, but let's see, where is my talk? Tem como botar minha transparência? Huh? Oh, it's here. Okay. Sorry. The talk should be a kind of informal. People should interrupt and... Okay. I can get here in the computer, but I cannot get in the screen. He's coming. But I'll be speaking about quantum turbulence in the BEC, because it's a little bit sour topic. We don't understand everything very well. And this is the week of Easter. And in Brazil, the week of Easter, we eat chocolate. So I brought some chocolate. And you can have a choice of white or black or both. So you sweet yourself before my talk, so you're not going to give me a hard time. You take one or two if you want and pass around. That is white, and this is a kind of a cookie for Easter. So, and if you have this, God promises that you'll be able to publish a nature paper, a science paper, and all that. So don't miss it. Otherwise, you may be in trouble. Okay, so my topic is on experiments and give some perspective of turbulence. And you can look any screen. I was requested by Professor Pisa that we should have a big one instead of a lot of small ones. But I hope you can follow what I'm going to tell you. And turbulence, we have an expert in turbulence in this audience, which is Makoto Tsubota from Osaka City University. And he's going to give us some taste for modern ways of looking and doing, he's also collaborating with the group from Cambridge. And so we're going to have two of those. And I think Randy Hulet also going to give us some talk about disorder in the 1D, more or less, which I believe is going that direction too. But so what I'm going to show you some of the experiments we do and give some motivation why we want to study turbulence in quantum fluids. You know, and we call that quantum turbulence because actually the fluid is quantum. And many people expanded their life in this topic, trying to show that actually it's very similar to classical turbulence or turbulence in classical fluids. Okay, so I am going to drop this. I have a big group in São Carlos with many faculties and many laboratories, and the BEC is one of them, and I try to list everybody here that are working. We have 3 BECs in São Carlos and probably a 4th one in Dysprosium soon. And Kuvia is already saying that the picture is not so new. But the problem is people comes and goes all the time. It seems that they come and go faster than I can take a picture of them. Anyway, we collaborate with a couple of people, including Tsubota, in some original measurement of momentum distribution, Carlos Barengue, Yukalov, Giacomo, Alex Fetter. I think theoreticians all know Alex Fetter. And also Randy Hulet in some aspects, not on the turbulence, but in other ones. Okay, so turbulence is important. You all know, we all hear about, but it's a very old topic. We are not discovering anything new. But in terms of understanding the scientific basis of turbulence, is still very young. It seems that this is one of the challenges we have. And American Physics Society, they place turbulence among the 3 challenges, either in physics or mathematics, that has to be faced in a serious way. And turbulence is everywhere. I always like to mention that life, the way we are product of turbulence. So Mattias, you should thank God every morning because of turbulence. Otherwise, the breathing that you do could not exchange the gases on the lungs. And the blood is circulating your body could not also deliver nutrients if the flux was all laminar. So you need turbulence in normally in the fluids that goes in your body to be able to exchange, because you all know that laminar flow has 0 flow at the walls. And because all those fluids are viscous, you do need turbulence. And some people claim that in the brain, part of it goes turbulent and part of it goes laminar. I don't know too much about this. So, and turbulence is what makes possible to live on the Earth. Otherwise, the layer closer to the surface will be filled with chemicals that we cannot take it. We have 2 experiments on this topic. One using rubidium-87, which is mostly what I'm going to show. And I don't think I will be describing how a condensate works. I'm going to start with condensates. And we have a second one, which is a mixture of sodium and potassium. And the idea here you can imagine is not to do fundamental mixture studies, but it's to use one species to be able to marker as one species to reveal what's going on in the other one. So this is the original idea. And we already starting to produce lattices of vortices and things. But you know, experiment like this comes and goes and takes many years to get in the road. And we are in the process now to mix both. And even though we already start some experiments with sodium. Okay, so when you speak about turbulence, in general, you need some ingredients. I apologize, I didn't know that I will have a small screen, so some of the things are the size of the letters. But to have turbulence, we need a couple of ingredients. We need the randomness, so we need conditions that produce kind of fluctuations on conditions, because you always, doesn't matter how you want to start always the same, but fluctuations will always take you to a different place. We need some dissipation. So somehow you inject the energy in the system and this energy has to escape. We need a cascade. So that is, the system has to have this ability to transfer energy from large to small scale. We don't go to shake the atoms, we go to shake the fluid. But somehow this energy has to reach many different scales. And this we call cascade. And we need scaling. So some of the things should be invariant by scaling space, time, and velocity. And because we require those things, if you start in classical fluids with the Navier-Stokes equation, and you request that the system be invariant by scaling, you end by extracting from the equation a relation that tells how the energy has to be when invariance is imposed to the system. And this is called Kolmogorov relation. It's an empirical relation. It comes by analysis and you get the equation. And it turns out that many experiments want to show that this is a universal type of behavior, you know. And some people, in my opinion, not so right, they assume that you need to have this kind of law to get turbulence behavior. But we deal with different systems. Like my system is small. A tank of helium is one thing, you know. A river of water or the ocean is another thing. I cannot have all the invariance that should be demanded by having turbulence the way that people originally think. And this is one of the things I'm trying to understand is how that goes in a finite closed system, which we don't have too many scales to play with, right? So we have a small range of scale to deal with. Just one thing concerning turbulence, and I think Tsubota also is going to show you this, is that in quantum fluids, the vortices are quantized. So if you take the velocity field and you circulate, you get an integer number of h divided by m. So the circulation is quantized, as you know, it's consequence of quantization of the angular momentum. And if you look at that expression, we know that the fundamental circulation, which means the integral of the velocity field around a vortice line, when you introduce rotation in the fluid, we will make vortices. And the integral, the stable one, is the fundamental, when you have h divided by m of circulation, which means h bar of angular momentum per atom in your fluid, right? And many people that has condensate, they introduce rotation, and then suddenly, when we have a rotation enough to give you at least one h bar of angular momentum per atom in your system, a hole pops up, which is the vortex, and is quantized. In classical fluid, this doesn't happen. In classical fluid, you can have anything you want. So this is already a good thing, because here, the vortex lines are quantized, so it's easy to deal with. We don't have to deal with a big variety of rotation. We have all the vortices, in principle, equivalent and obeying this quantization. So people believe that then we have a better chance to understand the turbulence in a quantum fluid than in a classical fluid, because there are simplifications that goes on in this situation. And of course, the center of rotation, the density goes to 0, and Pitayevsky solved this long ago. In fact, somebody told me that he formulated his equation that we call Gross-Pitayevsky to be able to represent vortices. This was one of the goals of Pitayevsky when they formulated this equation. And the size of this core is related to the density and the scattering length. And it's basically the healing length. This is the core of the vortex. And in normal fluids, we have a few quantum fluids that we can play in the laboratory, but helium is so dense that the healing length is too small, and it's very hard to visualize or to do some measurements with that. So you always do indirect measurement. Nowadays, they are able to put traces on the vortex line to be able to see what's happening. But in condensate, the density is not so high, so the healing length is big, and you can visualize the vortices. So this is a nice thing, because we can see what's going on in the cloud. The idea of turbulence in the superfluid is old, and it started with Feynman. Feynman proposed it, and was sooner after detected in liquid helium by Vinning, I think, right? Joe Vinning from England was the first one to detect the quantized vortices and that they could tangle. If I produce too many vortices in the fluid, they will start to tangle, they will react, they will produce what we call reconnections, and then there will be a evolution of the rotation I introduce, giving origin to the cascade. There are a few possibilities for the energy to flow in different scales, and this idea is going on for many time. And really, people work with helium. That is a big factory of turbulence in helium, you know, especially in Europe and the United States. And now, with the condensates, people understood that we could do equivalent things in condensates, and this was my goal. And there are many advantages to work with condensates instead of liquid helium. And here I more or less listed. Oh, and by the way, there is a review of the American Physics Society, the annual book of the American Physics Society, edited by Fujimoto, that is coming out in the coming months. And we wrote a very nice review. The limit was 20 pages, so we put everything we could in 20 pages. And this table is there with a better presentation. So here I put the classical turbulence, everything that we have, and the normal quantum turbulence that people are studying for decades, and now the turbulence in trapped superfluid, which is the condensate. And of course, there are a few advantages that we see, and that's why we got involved on this. There is a feature that's always true for this turbulence, is that energy has to be injected in large scale and migrate. So you gotta have a mechanism for this to happen. And people identify a few of those mechanisms. So I think Tsubota is going to speak a little bit about this. But normally we have a Richardson cascade. We believe that the vortices can make rings, and those rings react with rings, make smaller rings and smaller rings, and this makes the energy to go to a small scale. And there is also the Kelvin cascade, Because when two vortex line, you may believe that they are straight. When they reconnect, this is like avoiding crossing of levels. You know, they get reconnected, and then you start to have wiggles on the vortex line itself, and more reconnection, more and more wiggles, until you reach the atomic scale, and then you have phonons. And those are the ways that energy migrates to lower scale, you know, smaller scale, and energy will be dissipated there at the end. I've been in this since 2009, motivated by Tsubota. He published a paper saying that if I rotate a condensate this way and that way, I will generate vortices in one direction and the other. If I only generate vortices in one direction, they crystallize. This is a Brikosov type of lattice. But if I produce in two, they will react. And motivated by Tsubota, just the year after, I think, right? We did an experiment that we shake the condensate. So we introduce tiny rotations and squeezing, and that generate vortices and that evolve. And this is, everything here is things that we somehow are doing. And I added the granulation, which is something that we did, this granulation. We see that at the end, the system are breaking islands that we believe we never were able to prove. They are islands of superfluid, and we still did not prove very much, but Randy went to a 1D in another direction, and I also saw some evolution from excitation of Faraday waves to granulation, so he's going to tell. And I'm going to give an overall, the thermodynamics. We want to do a kind of thermodynamics, but this system is not homogeneous. So we formulate, together with some collaborators, a global thermodynamics that Marcos is going to present on Wednesday, some of the measurement we have. But the idea was to come and try to measure compressibility in a turbulent cloud. But we did not succeed at the moment because we don't have good ways to map the 3D density. But maybe this year will be a good year. So I'm going to just give you the things that are in red for you. The other ones are published. And I always like to say that we have also a nice physics reports combining together everything until 2017 that we knew. Now is a little bit out of date, but the review of the APS will come with more stuff. Okay, so there are different types of turbulence. So we have the Kolmogorov type of turbulence, which is equivalent to the classical. And some people believe that if many vortices cluster together, we make bundles of vortices. And then they obey equivalent to what people know in the classical. And they claim that this we could call Kolmogorov type. There is another one that the vortices are individual and reacting, and this we call superquantum turbulence. And is given by Vining, this guy from England, which is one of the iconists on these measurements of quantum turbulence in superfluids. And then there is also wave turbulence, which is we excite the condensate and we have those waves and very nonlinear interaction among them, and you produce random fluctuations of density and phase. And actually in the lab, we believe the system evolve and may pass to many of those stages. You know, it seems that mechanism will make the system to evolve from a vortice type of turbulence, which is a kind of hydrodynamic turbulence, maybe to wave turbulence. And I already told you this, and one of the important things in dealing with those systems is measuring the energy spectrum, because this is what people are able to calculate and to verify if there is this power law on a range of momentum, which is the Kolmogorov law, but does need to be the -5/3 is the law. And this range of scaling or momentum, where this law is obeyed, is co-inertial range. In this range of momentum is interesting because people claim that the energy migrates from scales without being dissipated. So energy in flows to this path and leave it out. Okay? And this is what is the challenge. One of the challenges now is to really measure the occurrence of this cascade in this range and be able to see what's the dynamic of all this. And Navon and Tsubota gave a first step, because for this we have to measure things in situ and have to be able to get the spectrum of energy in the reciprocal space to make sure that is taking place. People study liquid helium in many different ways, always by shaking objects, because, or maybe rotation too, but normally they shake a wire. Around the wire, you produce vortices. You put another wire, you have a current. You know, you put a current in a wire, in a DC field, a AC current, you shake the wire, or you put a field and the shaking of the wire will induce, so you detect and produce shaking objects in helium. And this is how people survive in doing this for a long time. But we obey some of the other stuff, and we don't do the rotation. Now we do in the combined species, we introduce rotation. So it's like coming with an extra laser and make the condensate rotate, actually. And we would like to follow Tsubota's original idea on the rotation in two directions. We may now do with the two species, but the way we did is what I call a washing machine. We introduce, if you go to the washing machine and you look, it doesn't rotate, but produce a lot of turbulence, because you give it tiny little kicks and that produce. And you can do that with your cup of coffee. If you start to squeeze and shake a little bit, the energy flows so fast that drops will spill out, get so much energy that's coming out. Okay, so we do what I call a atomic washing machine, which is a composition of squeezing a little bit. This is very tiny, you know. What we do is go shaking all directions and squeezing a little bit, and this generates vortices, as you can see in the picture on the top. We generate 1, 2, 3, many vortices, and if you keep pumping energy, they're going to react, and they're going to evolve to a very perturbed cloud, which has the properties of being turbulent. And this is more or less an artistic picture. You know, my pictures is always drawing by hand, and the students' pictures is always artistic, because they manage much better the cameras and take the absorptions. But the idea is you see on your left a single vortex in the cloud, and on the right you see the turbulent cloud. I just forgot to tell you that the sequence is produce the condensate, shake, wait a little bit, do time of flight, and detect. And then we do all kinds of measurement we can. This is an evolution going from a turbulent to something else. With Natalia Berloff, believe that this is an evolution from vortices to wave turbulence. And they claim it's possible. And then Yukalov from Dubina also believes that maybe I start with vortices, but sooner the system evolved to pass to a sequence of types of turbulence, right? Okay, and the system always behaves like this. We start to produce vortices. Remember, my system is not big. I have about 10 to the 5 to 10 to the 6 atoms in my cloud. It's a few microns across. We started to excite. Number of vortices start to increase. And then try to level out. I can't afford any more vortices in the space I have. The vortices start to evolve. And then the turbulence is established. And then if we keep looking, we're going to see, we don't see any more vortices. But we see a big resulting fluctuation of amplitude and phases.
Have you
No, I didn't, but now with the new system, the idea is to control the scattering length. Yeah, that's one of the ideas that we're going to pursue. Oh yeah, if you go to 0, something funny happens. I get an ideal Bose gas. I should be unable to do all this. And if I go to infinite, either I should be in trouble too. So that is a nice range between 0 and infinite, right? So we call that this is the optimal range to work, right? You know, normally we work in narrow range of things, but here it may be able. But rubidium is very hard to control the scattering length. So we associate with Randy because he's one of the best guys to control scattering length I know around the world. And now we're doing potassium 41 with sodium, and we should be able to control not only the interaction among the same species, but between different species, which is something interesting because we are able to study how thermalization takes place in those systems and so on and so on. Well, the theory you can ask Tsubota because he's considered among the 3 most prominent authorities in quantum turbulence in the world, following the page of the American Physics Society. So he's the guy. Okay? So, and he's here, so you can ask him the challenges of theory. But most of they do goes in mean field. This is a little bit annoying, right? Because there is a moment that we break down the mean field. We all know that. But they are able to reproduce quite well. And one of the excuses I give is that our system still preserve coherence. And then, you know, you see the vortices, you see everything that evolved. So mean field seems to be good, and Tsubota is one of the pioneers in simulating all this kind of thing. Here's a diagram, you know, I consider old because we produce a diagram showing that what we observe when we vary amplitude and time of excitation in this system, no interaction, maybe there is more access to be put in this plot, and then we go from individual vortices, which means we have a vortex and no turbulence, and then a domain that turbulence seems to appear, and then a domain that we call granulation, but we don't really know what that means yet. And that one we could not explore so well, and maybe in the coming future we're going to know what's happening. We have 2 ways to measure the energy spectrum. One is by time of flight, because in your system, time of flight is nice because it reveals the momentum distribution. Of course, this momentum may have different sources. The interaction among the atoms is one, but the amount of kinetic energy is another. And we already more or less proven, this is more or less a good consensus, that if you have a condensate that's turbulent, it's not in the Thomas Fermi regime anymore. This is a kinetic dominate state. So most part of the energy is in the rotation form. And therefore, the expansion should give us a nice view of the momentum distribution. Another way is by power spectrum, right? Power spectrum is you look correlations, it's like the astrophysics do. You know, they look at the black hole, they see a big image, they do correlation, they do all kinds of things, and extract from there information that is not so much visible. And in engineering, they use the power spectrum all the time. They do correlation, either in time or in space, and extract from there the energy spectrum. And this is what we do. We use these 2 forms. And of course, if you're going to use power spectrum, there is a very powerful theorem that's called Wiener-Cincini theorem that converts the second-order correlation to the power spectrum. And if you do time of flight, you let expand, you search how many atoms are far from the expansion center, and then you know how many atoms has a class of momentum. Normally you project, but there is a nice book on this that explains that this is fully valid. You can measure the projection of the correlation, and even though extract the 3D information. And I'm using this, and you have to do an Abel type of transformation on this. But at the end of the day, if we do everything right, we get the momentum distribution. And of course, the integral of the momentum distribution for a k square h bar squared divided by 2m, which is the kinetic for each momentum class, give you the total energy spectrum. And this is the kind of momentum spectrum we measure. And the left color plots are the plots that show a few vortices in the cloud. So even this technique is not fully good in there, but you see that you don't see any different from features from the condensate itself. But once the turbulence is established, you see the momentum migrating to higher, you see the distribution migrating to higher momentum, and there is a small range where a kind of linear behavior appear in a range of momentum. This is a D-log scale, right? So and we measured this some time ago, and we saw that the momentum distribution should have a -3 type of behavior. And from there, you take that what is the dependence with the energy. And it's not -5 thirds as predicted by Kolmogorov. Yeah.
You know what that peak is?
This peak? This is the moment. Oh, here we didn't put all the scales, right? Yeah, this is because all the momentum is this one? Oh, this no, I don't know what it is. No, I don't know what it is. In fact, this tail here, I'm going to show you in a moment details on the tail of the distribution. So normally, to measure the momentum distribution, we restrict ourselves to the inertial range. Is where the cascade should take place. But then we're looking for other things nowadays, and we find a very interesting thing. So we measure, and we measure also in the power spectrum, using the power spectrum, which is expanded, do the second order correlation, and people are using this already in helium, right? So there is already a publication in helium in 2014, and we are finishing our publication now. You know, you have to battle a lot of times, and this is how it goes. And the way to do, I'm sorry, I'm not going to explain very well, but it's exactly the way they do in astrophysics. Many shots, statistics, remove the average, gets only the big fluctuation, do the second order correlation on the amplitude. From there, extract the Fourier transform, and get finally the spectrum. And I can give you the preprint if you want. It's not accepted, the paper, so I'm still convincing the people. We are in the second turn, running in the second round, but it's going well. And then, of course, you measure again the momentum. I like very much the power spectrum because we have a much better signal, much better resolution, because it seems to me that correlation is always powerful stuff to have. And you can see our system is not isotropic cloud, it's not isotropic. But still, we get the same law in all directions. And I think the amount of excitation in each direction, or the amount of migration of momentum, the cascade happens in both, but they happen in a different way. I believe, and I consulted Tsubota, he thinks this is fully possible. Because people always complain that turbulence should be isotropic. And I'm claiming that maybe not in finite system, in systems that are not isotropic, and I never start with an isotropic excitation. So I put vortices in specifically a few directions. I should not expect the energy migrate equally in all directions. So, but this is still a debate. It's one of.
I don't think the turbulence should be isotropic. It depends on the case. Yeah.
But your colleagues referee, they normally claim that should be isotropic, right? And this is a problem that we try to convince. And this is one of the measurement. We do have a power law in both directions in different range, because my system has different range in different direction. I should expect different behavior. And I think I agree with you, and you agree with me. So we keep being good friends.
Geometry, how they set the system.
Depends, exactly. And I'm gonna, if I move, there is a little move if I, okay, so we measure this. Of course, there is a range of amplitude of excitation that this system doesn't work because I don't have a full random distribution of things. But whatever I reach the amplitude where we always claim turbulence will happen, so excite for a fin time. Both methods converge to the same dependence on the momentum for that range of momentum. So it, I think, is a proof that we are reaching a cascade, right? Okay, now our numbers are, let's say, in agreement with what the theoreticians predict for a wave turbulence, not a turbulence with the vortices. But again, what we believe happens is the system evolves. The final stage of this development, maybe the vortices disappear, they cannot survive in this big reaction, and what we end by having is big fluctuations. Or we have the Wiening turbulence, which we cannot identify the vortices anymore because they already went to the cascade. And they both predict that we should have a n of k around k to the minus 3. And this is still, we're going to do more measurements to prove how is the evolution of the turbulence in such a systems. Okay, well, and then we made some, I'm going to skip the entropy part, but clear there is an entropy build-up after the turbulence is reached, right? And we use the definition of entropy, which people use for many things, which is the Shannon entropy, which is valid, and people use that all the time. And clear, you can see. And now I'm trying to see what is the rate of entropy accumulation on the sample, because there are some irreversible process, and if you know that, you can get some characteristic of irreversibility and things like this in the quantum system. Okay, now, I want to do two applications of turbulence. We want to understand a little bit the turbulence, but I want to give you two very nice applications before my time ends. Mattias, how I'm doing? It's 1 hour total, so you should restrict it to 50 minutes mostly. Mattias, you German, you can. But I'm Italian, so I will escape. Okay, but now it will be fine. Yeah, okay. So I'm going to show you two things, and the idea is very simple. The first idea we had is we're going to have the turbulent cloud and let expand. So this is a still matter wave, but it's a collection of amplitudes and phases, maybe distributed in a random way. I don't know if you know enough optics, but when you take a coherent laser beam and you shine it to a rough surface, the scattering produces a multiple interference that give a very interesting pattern, which is called speckle. This speckle pattern is a random distribution of amplitudes and phase, and people that do statistical in optics, they know very well, and this is a very nice sample to merge statistics in the field of coherent waves. The idea here is simple, and this paper was already published, and Hussein is one of the collaborators. He characterized the chaotic part of it, and is publishing the proceedings of the National Academy of Science in the United States. And what I do is I produce the turbulence, and I let it expand. And I try to investigate this matter wave, this condensate, turbulent in expansion, is like the propagation of a matter wave, right? And I analyze the speckle characteristic of it. I know that many people are speaking about speckle of matter waves and so on. This is one of more speculation of this, okay? And this part was very nice. And you all know that a coherent laser beam, when it's propagate, there is a diffraction. And the diffraction depends on the waist. If you squeeze the beam, if you have an elliptical Gaussian beam, it is going to expand faster on the squeezed direction, right? We all know this. And That's expected the same with matter waves. So matter waving expansion, you know, if there was a pure condensate, which is what I call in expansion, which is what I call a coherent expansion of matter waves, it behaves very much like a laser beam. Okay? It's expanded faster on the direction that's more squeezed. If I have a turbulent, we realize since the very beginning that this doesn't happen. It keeps the shape. Alex Fetter called this a self-similar expansion. It turns out that if you go to a speckle, if you create a speckle beam, you scatter in the surface, you produce the speckle field, and you let propagate. It has the same behavior. It does not diverge as a single coherent beam, because now the coherence is in the domains, not in the whole thing. So exactly what's happening to the expansion of a turbulent cloud happens to a speckle field. So that original phrase of Eric Cornell, that a laser beam is for light, what a condensate is for a normal gas, this is like another proof. We have many proofs, but this is another one, because the speckle can take place, and then of course you're going to understand everything, because if you take a coherent laser beam, the divergence is given by the wavelength divided by the waist. This is a well-known stuff, right? If you write down the equation of propagation of the laser, that's what you get. And the speckle field, the divergence is the wavelength of the light divided by the coherent length. And the coherent length is, in the other case, is the waist. But in our case, is the domain, so doesn't happen. That's why the speckle field propagates, keeping the shape of the beam. And that actually happens in the BEC. And we did the things to compare the BEC. This is the aspect ratio, the dimension of the beam as it propagates in time, and the aspect ratio. This is the turbulent and the non-turbulent BEC, and this is the optical beam propagation, the coherent beam propagation, and the speckle beam propagation. And we calculated the second order correlation, which here is density. If you go to people studying speckle, they do intensity correlation, which is equivalent for us. And if you do that, I'm not going to elaborate why you have the peak and everything, but it turns out that the light and the matter waves has equivalent second order correlation. And the size, the correlation here is more or less the size, the domain of each of those bright spots that we have. This is well known for speckle, and is fully equivalent, I claim, for the matter wave originate from a turbulent BEC in expansion. Okay, so this is, we have proved this, we made many characterizations, and we even explain why these expand in a self-similar way, make a comparison with the optics with coherent waves, and I think people accept. But I think what's very interesting is that this may be, you know, a way of combining the matter wave, the quantum turbulence with statistical atom optics, which I think is a field going on, but still not well established, because you know, they don't have all the richness that we have in light beams, right? In light beam, we can do all kinds of things. And in matter wave, there are many people that claim in beams that they produce speckle, but I think this is, it's very hard to believe that they have speckles on those experiments. But here, I think we do, and more than that, maybe this is the first demonstration, at least what I claim, of a 3D speckle wave. It's not easy to produce optically. They have a few ways, they claim, but in matter waves, it seems to be natural. We're going to produce, normally a speckle field is 2D, right? It's in the plane. Now here is a 3D. You have to consider a 3D. So I think it's nice. Fortunately, some people from Newcastle, Nick Parker, he's told me he's interested, and he's coming to Natal next June and in a meeting on quantum turbulence, and I hope we're going to really start. And I measured this, and then I went back because I need to do some other things. But now I'm going back because I receive once in a while people with suggestions on the paper that we publish. So it seems that there are some interest. Now I'm going to do a second application, which I would like to do in situ, but I can't. I'm still doing expansion. I'm going to look to the very long tail of the momentum distribution. It's beyond the inertial range, okay? So I'm going to look at the tail, long tail, higher momentum atoms that could be thermal atoms around. But we never start with so many thermal atoms in that momentum, so it must be product of the turbulence and mostly from the cascade. So if you look the condensate, you see the profile of the density after expansion. And again, I'm claiming we are mapping momentum distribution. If we start to produce the turbulence, you still see the tiny little bump there, but you see the tail is starting to become exponential, not Gaussian. And exponential velocity distribution or momentum distribution is something very interesting for quantum systems because it means absence of thermalization or maybe localization. And so this is just to tell you that normally the blue interval is where we look for the inertial range. We look for the power law behavior in the momentum distribution. And the red one now is where is the tail, is the long tail. Is the cloud that's really external during the expansion. This is where we look, and clear, you can see that it's not following the same law of the top one. And if we look, that's exponential. So that tail, before really reaching turbulence, is a Gaussian, as we all know. The high excited atoms obey a Gaussian distribution in momentum because they are thermalized, right, with whatever is there. Now, when that changes to exponential, means something is going on. Angela White, which is a lady in turbulence, she claims that a turbulent superfluid should have exponential velocity distribution. She published a nice physical review letter a few years ago. But I claim maybe this, because the absence of thermalization, but maybe something else. And this is the transition. This is as a function of the amplitude of excitation. So you see clear. You see this alpha exponent, if it is 2, is a Gaussian. If it changes to 1, is exponential. And we do this in many, varying everything, like all experimentalists do. You change all the knobs, you collect the data, and we see in what moment of excitation it turns to be exponential, the very long tail of the distribution as a function of the condensate fraction. So you see very much that this is related to the presence of a decent condensate. Otherwise, it doesn't happen. You have more thermal atoms, and this doesn't happen with thermal atoms. Okay, so we did all this investigation, and maybe Angela is fully right. This is just consequence of the non-thermalization. 5 minutes, okay, yeah. But I believe that maybe what's happening is I have this core, which is turbulent, and I have this cloud of high momentum atoms, very non-dense. The density is like 10 to the 3 times lower than everything else. They don't interact very much with each other. So they have all the ingredients to interact via mean field with the core, turbulent core. And then they will have a multiple scattering in this turbulent core. And then they will produce a localization. So in fact, if you see the transitions of things, looks very much the same. And my idea is this, is the mean field after turn off, let expand, the mean field, which is turbulent, which has random peaks everywhere, works like a random potential for the high momentum atoms. And then they change their behavior. And the exponential is away. And then we try to show that they really hang around a little longer. And well, I did many things to try to justify that that could be it's not a many-body localization, but it is an interesting system. Produced is a self system where you have this superfluid turbulent surviving with a cloud of high momentum atoms that originate by the process itself, because by a cascade, and they do localize. Well, the referee didn't like, so he asked me. He said that maybe he's going to consider the publication, but I have to drop the word Anderson localization. So I drop. The referee is always right. But I still believe that something is there, because it's very interesting. I didn't show you the diffusion I measure, and it's suppressed by a factor of 3. This is already interesting, right? And I claim, well, this is exploratory. Maybe I'm wrong, but people have to know that this is here. And they can, theory. We need a theory, because this is a very interesting system. You have a tiny expansion of the core, but then you have this cloud. It's a dynamical system. It's not like a random potential where the atoms comes ring around, which is the normal system for exploring Anderson localization, right? But, and then we did many other things we're doing now, like try to naturally produce turbulence from a large vortex decay. And this is nice. We can understand how turbulence is proved. I don't know how to click here to finally produce a, let's try, right? Doesn't go. So it doesn't go. I was going to show you how spontaneously a large vortex, a vortex of larger circulation, decay, and spontaneously make the system go into turbulence. This is another interesting thing, because in classical fluids, the system doesn't go alone by turbulence. You have always to drive. But here, if we produce a large vortex, the system machine is quiet. But during the spontaneous decay of a large vortex, you generate turbulence. And, right now we are trying to measure perspectives, putting a leak on the trap and make sure the high momentum atoms will escape. And by looking the losses, we infer about the energy distribution inside. Navon, with the help of Tsubota, making the calculation, they already produce a nice work, which is, I'm not depressed by that. I'm even more interested now, because I believe this is an indication that we'll be able to really measure cascade moments in situ on the condensate. And the isotropic aspect, now we're going to focus also in show people that by correlation in many directions, we do have the turbulence, even though does not need to be isotropic. Thank you very much.
Thanks, Wanderlei. So now let's have some discussion. There's questions. You want the mic?
I think you need a microphone because they are broadcasting.
Yeah, I'm not so familiar with the quantitative description of speckles. So what is the way you tell if you have speckle or not? What's the quantitative criterion?
Well, normally when you study a speckle light field, which is mostly what you do the correlation. So you do this exactly the way I do. You do the correlation and you can find the correlation length. That has to be equivalent to the domain, okay? And then you make sure that what you do have is a collection of, if I have to describe a speckle field, will be a sum of amplitudes and phases, right? But random distributed. And what the people normally study is what is this statistic of this distribution. And that's the way people normally do. And
There's randomness, but there's also regularity.
regular, yeah. And in each domain you have coherence, yes. But the phase is fixed, the phase between one and the other. But you don't know what it is. It's not fully fixed.
I think basically speckle light. Oh, sorry. The speckle light is like a laser, laser beam, which is divided through several complicated diffraction and whatever into several laser beams, Basically, that's what it is.
Yeah, but they evolve.
But it's very complicated.
If you look at, because the speckle originates from the interference. So if I produce a speckle and I look at this plane, I see one pattern. If I go here, I see another pattern. Okay? This is, but people, that is, let's say, the investigation of this random characteristic of light that they call speckle field is well understood in many aspects. And people are still studying and they apply, right? Because they use the speckle to measure. Today, speckle is a very nice tool for measurement, even in the heart, birth, or the circulation in the brain. They do speckle spectroscopy and they find a good thing. Yes, Randy?
I just wanted to say that people use speckle to imprint on Bose condensates to study localization phenomena. So it produces, by random phase, it produces a random potential. It's basically a sandblasted piece of glass in which the light is transmitted, but there's a phase imprinted on it.
Is there more questions? I hand you.
Thank you. Speaking about randomness, I was very curious about your Anderson localization. So in mesoscopics, people understand that Anderson localization is highly favored in 1D. It's marginal in 2D, and in 3D is hard to say. But a key ingredient is always quantum coherence. And I mean, your system, I understand, is small, but 3D, and it's fully quantum coherent all the way down?
Anderson localization is a single particle effect. So I have those high momentum, let's say, partial waves, which are the atoms in high momentum, and they scatter they interact, right? This is the mean field. So I don't know why I don't have all the ingredients. I think I have all the ingredients there. And in fact, you don't need a coherent sample of light to really, if you are able to show that, or a coherent beam of atoms, if I am able to send one atom per time, or even a few atoms, they will hang around, they will multi-scatter and destructive interfere, so they're not going to escape from that region so easily. This is what people use. So I don't think it's missing any ingredients, but I agree with you. There are missing elements, and maybe the referee is right? It's missing some ingredients to prove that this is so. It is not. I mean, it's not right at the moment to speak about the Anderson localization. But, I mean, this is an exploratory idea. It may prove it wrong or may prove right. So this is...
Yeah, I was also wondering, you're applying these momentum distributions at high momentum, but you didn't mention the tan contact. Does that picture break down immediately, the 1 over k to the 4th expected from the tan contact? As soon as you're in the turbulent regime, do you lose that?
No, I didn't explore that, but I believe that maybe we lose that, yes. But this is a boson system, huh?
You can have
you can have the contact in the boson
for the boson.
I didn't explore this. I don't think I can tell you if I lose or not this edge stuff on there. So sorry.
Any further questions at this point? Okay, let's thank Wanderlei again. Coffee break. Yeah, now there's a coffee break until... Okay, so I hope you had a good coffee break, and we are all prepared now for Randy Hulet's talk, Excitation of Bose-Einstein condensates from Faraday waves to granulation. He's from Rice University. Looking forward.
All right, thank you, Mattias. It's a great pleasure to be back in Brazil. I have many old friends, and it's great to see them, and a lot of friends that aren't so old, but I've known a long time, and it's good to see them as well. So what I'm going to talk about today is actually a collaboration between my group and Vanderlei's group. We've been working on a topic for the last few years involving the modulation of the interactions in a Bose-Einstein condensate. So how do I adjust the picture. Do I use this thing? All right, great. So this is an outline of what I'm going to be talking about. So I'll first talk about the excitation of Bose-Einstein condensates by modulating the interaction. We do that by modulating a magnetic field near a Feshbach resonance. And then I'll talk about a couple of applications of that technique, one to the observation of Faraday waves and the other to something that we've called granulation. So the idea is that you have a Feshbach resonance, and we work with lithium-7. So there's a very strong Feshbach resonance, which is shown here. There's a scattering length that's strongly dependent on magnetic field. What we show here is about 7 orders of magnitude of range in the scattering length, going from scattering lengths of order a few tenths of a Bohr near the zero crossing to 10 to the 4th Bohr, or even maybe even greater when you get very close to the resonance at about 740 Gauss. So the idea is that with the equation over here on the left is basically giving the essence of that, is to modulate the magnetic field, which we do sinusoidally, and that gives a sinusoidal modulation of the scattering length. That actually was an idea that goes back to Sadhan Adhikari, who I think was at this institution, if I'm not mistaken. The other one. Ah, okay, but also in Sao Paulo. Yeah, is he still there? Ah, so yeah, so anyway, I want to give him credit for the idea, and also almost simultaneously another group of people, Panos Kavrakaitis and Boris Malamed and others, who realized that you could modulate the interactions just simply by modulating the magnetic field. So in this case, the scattering length directly couples to the nonlinearity in the system, which is very similar to modulating the trap potential. For example, the radial trap potential, which squeezes the condensate and therefore modulates the interaction as well. But this does it in a very direct way, and it doesn't necessarily need to change the density. So we're going to explore the dynamical response of periodically, sinusoidally, modulating the interactions in various frequency regimes. And I'll show you get very different physics depending on the frequency of the modulation relative to other frequencies that define the system. So the first thing we did, and this is actually an experiment, one of the first experiments that Vanderlei and I did together, this is about 2010, I guess, about 10 years ago, where we modulated the magnetic field near a quadrupolar resonance, near a resonance of a normal mode of the system. And so the mode that we chose was the lowest quadrupolar mode. It's the out-of-phase modulation. So the condensate is squeezed in one dimension and then expands in the other, and then is squeezed in the other direction and expands in the other. So it goes like this. I have an out-of-phase quadrupolar mode. That has a frequency which is very close to the axial trap frequency. So on the order of square root of 5/2 up to twice, depending on the strength of the interaction, whether you're in the Thomas Fermi or in the non-interacting regime. And what's shown on the right is the result of that for this quadrupolar mode. The blue is the quadrupolar mode, the red is the drive. And you can see the modulation frequency peaks up at a value which is 10 hertz, which is very close to the modulation of the quadrupolar mode, which is at about 8 hertz, about 8.2. So the square root of 5/2 works out to be about 8.2 hertz for the trap frequencies that we have. So you can see the method very powerful to be able to excite these normal modes and to be able to measure their frequencies as a function of various parameters that define the system. For example, the density or the number of atoms in the system. We then moved on more recently to looking at something that are called Faraday waves. And this is unbelievably something now which is a topic that's 200 years old, goes back to Faraday in 1830 or so. in which he took a bucket of fluid and modulated it sinusoidally, vertically, in the presence of gravity. So he modulates this bucket, and at certain frequencies, he saw these amazing patterns, some of which are shown on the right. These are not photographs from Faraday, but these are experiments that have been done subsequently. And you can see very diverse patterns, very rich, annular patterns or radial patterns that can follow depending on the various parameters of this system. Things like the type of the fluid, its viscosity, the shape of the container, the frequency and amplitude of the drive. And it turns out that these things can be explained or calculated by the Navier-Stokes equations, with some approximations to the Navier-Stokes. And in particular, these waves are surface waves. They're just on the very tip of the fluid, and they're very, very shallow, and they're essentially standing waves. So they're waves that persist for long periods of time, even after you shut off the drive, depending on the viscosity of the system. And these Faraday waves, turns out, can exhibit chaotic behavior. I'm not going to get into that, but chaotic behavior actually in turbulence that would connect, I think, with some of the things that Vanderlei was talking about in his talk. So Faraday waves are particularly interesting in superfluids. And why is that? Well, the damping is small in a superfluid, and so these patterns can persist for long periods of time. They also may dissipate by the formation of quantized vortices. So it's possible to modulate a superfluid, for example, liquid helium-4, which is shown on the right. The figure A is just the surface of the quiescent fluid, and as it's modulated, this is a group in Japan who did this about 20 years ago. When you modulate in just exactly the same way that Faraday did, you modulate it vertically in the presence of gravity, you see standing wave patterns on the surface of the superfluid. And these patterns may dissipate in the formation of quantized vortices, and that was observed as well. So also more recently, by Peter Engels, took an elongated, essentially one-dimensional Bose-Einstein condensate and modulated the condensate at frequencies that are closely related to the radial trap frequency. And he found, almost very, very reminiscent of Faraday, he found this standing wave pattern that's produced by excitation of sound waves in the system. So by modulating it near the radial trap frequency and coupling to the nonlinearity, you produce sound modes, phonons, that propagate through this condensate axially and produce this standing wave. So it really is a standing wave. It's not really a normal mode of the system, but rather something a little different. All right, so we've also been exploring Faraday waves in a lithium-7 Bose condensate, and we did it in a somewhat different way in that we modulated the Feshbach resonance to modulate the nonlinearity instead of the trap frequency. And we would modulate for some period of time, which we're calling TM, modulation time, and then we wait for a hold time of something like 20 milliseconds or so. And what's shown on the bottom is what we see. So you see, as did Peter Engels, this standing wave that persists for a long period of time. Even after you've turned off the modulation, you still see this standing wave pattern that is unchanged. So in this particular case, the average scattering length was about 4 Bohr, and the modulation depth was about 1 Bohr. So you can see that it's a very weakly interacting condensate, but a very elongated one, almost one-dimensional. And the modulation depth is very, very weak. So we're modulating it very gently to do this, and only for a few milliseconds. So in this particular pattern, I think the modulation time is about 5 milliseconds. And you wait for about 20 milliseconds for the density to respond, and then you observe this standing wave pattern. So we analyzed it by doing a Fourier analysis of the pattern. So we take the density distribution, we integrate along the radial, one of the radial coordinates, get a one-dimensional line density, fit that to a Thomas Fermi distribution, and subtract that fit to get something which is just a model of the modulation itself, just the density modulation induced by this standing wave pattern. And we took the Fourier transform of that, and that's what's shown on the right. So on the bottom of this axis is the spatial periodicity, or the spatial frequency. And for this modulation frequency, you can see that the modulation is about 10 microns. The wavelength of this modulation is about 10 microns. This is a parametric resonance. So we're driving it actually at twice the radial frequency, not at the radial frequency itself, but at twice the radial frequency. And a standing wave pattern then oscillates its amplitude at the order of the radial frequency itself. So it's very much a parametric resonance, which is exactly what Faraday saw in his case as well. So this can be worked out in a variational type theory. This is a theory that we're comparing, was done by Alexander Nicolin. And he took this ansatz for the wave function, the modulated Gaussian, and he obtained a Mathieu type equation, which you can see on top of the plot, a Mathieu equation for the amplitude of this wave. So the oscillation of the radial frequency drives the growth of this amplitude. In the first two modes, you can see there's several modes that are present. There's a very large mode at twice. This is the parametric resonance at twice the radial frequency. There's another mode, a secondary mode, that Alex calls the resonant wave, and that's at a frequency equal to the radial trap frequency, equal to omega r. And they're really, at least on this scale, in this color depth, those are the only two modes that you can see, and experimentally, those are the only two modes that we can see as well. There are other modes. If you look very closely at very close to the edge here, there's a mode right there which follows a pattern given by the Mathieu equation for the stability of the Mathieu equation. All right, so for now, we'll just focus on these two modes, the Faraday mode, which is the dominant one, and then the so-called resonant mode, which is the non-dominant, but resonant rather than parametrically resonant. So we can actually see both modes observable in an FFT if we modulate at frequencies that are near this resonant frequency rather than the parametric frequency. So this is a frequency of 200 hertz, and the trap frequency is something like 450 hertz. And so this is on the order of half of the trap frequency. And you can see a primary mode in the FFT, the one indicated by the blue arrow, and that's the parametric resonance. And then there's a secondary mode, which is shown with the red arrow, which is this so-called resonant mode. And they're both present, and if you plot the spatial frequency as a function of the drive frequency, you can see various things. So this is the parametric resonant frequency here. So this axis, if you can't see it, goes from 0 to 2,000 hertz. The parametric resonance is about 900 hertz or so, twice the trap frequency. It's very, very strong. You barely have to modulate it at that frequency to be able to see the growth of the standing wave. And as you go away from resonance, you get a spatial periodicity which goes like 1 over omega r for the dominant mode, which is in blue, and the secondary mode, which is in red, is secondary except right on resonance at the trap frequency omega r, and then that one dominates. So we also looked at the interaction dependence of the Faraday wave. So this is plotted against an interaction parameter, which depends on the effective scattering length, A bar, the average scattering length, times the 1D line density. And the solid line is Nicolin's theory, and it's just bang on. There's no fitted parameters to this. So the theory is really, really good, both in this density dependence, but also the frequency dependence that I showed previously. So one other aspect of this, which is that we can study, is how this mode grows, how it grows in time. What are the dynamics of the growth of the Faraday wave? So again, we're modulating at the parametric resonance, 2 omega r. We modulate for a very short amount of time, about 5 milliseconds, and then we wait for something like 20 milliseconds for the pattern to fully develop, and then we look at the amplitude of the FFT at the parametric resonant frequency. And what we find is that it grows initially and gets a peak at about 20 milliseconds, then decays again, and then followed by another growth, and then a decay, and followed by another growth, and so on. And so what we realized was happening was that as we were exciting this parametric resonance at 950 hertz, there was also an excitation of this slow quadrupolar mode that I started off showing at first, and this quadrupolar frequency is just something like 8 hertz. So they're far, far from resonance, but nonetheless there's coupling between this interaction modulation and at 900 hertz with this quadrupolar mode at around 10 hertz. So the red line is just the sinusoidal fit of the Thomas Fermi radius in the long, axial direction. It's oscillating very, very slowly at the same time that the Faraday wave is developing. So this growth and collapse phenomena is due entirely to the fact that the size of the condensate is changing and very slowly, but that governs totally the dynamics of the growth of the Faraday mode. So the Faraday mode is there, it's fully developed at 20 milliseconds, and the quadrupolar mode then begins to oscillate at something like 10 hertz, and we see this growth and decay and the growth and revival of this Faraday pattern. So this is shown here in this, if I can get it to work. Let me see if I can. So this is a cartoon. These are images of the FFT amplitude and how it initially grows at 20 milliseconds and then decays at about 100 milliseconds and then grows again. And that's all because if you look above, you could also see the longitudinal size of the condensate was oscillating at the same time that the Faraday wave was developing. Okay. So one of my, the question? Yes, Pablo.
If I understood correctly,
yes.
The Faraday wave is adapting to the boundary conditions on the condensate.
Yes.
But that's changing with
yes.
the quadrupolar dynamics.
That's right.
Just adiabatically?
So I think, yeah, so I think it is, but I don't think that's me. Oh, there we go. Maybe it was me. Yeah, so I'm not sure how to answer that question. So certainly the slower axial frequency has got to be adiabatic, but it affects the growth of the Faraday wave in that the density is changing at the same time. So then you're way off resonance because the nonlinearity is changed. And so even though it's an adiabatic change, if we could follow with frequency, you're probably right that we could see that mode go to change to a different frequency, change to a higher frequency. But that's not the way the experiment is done. It would also be difficult for us to be able to resolve it because even the condensate fully extended, the frequency of the modulation, the spatial frequency is about 10 hertz, or about 10 microns. And we wouldn't have the resolution to go below that at higher frequencies. So we did a Gross-Pidievsky simulation, and my student was able to calculate using Gross-Pidievsky the FFT amplitude of the Faraday wave pattern, and he found the result is in here in blue. This is the FFT amplitude after 5 milliseconds of modulation, and then this is hold time out to 70 milliseconds. And what he sees is there's a very significant component that's oscillating quickly, and this is the radial density which is actually doing that. But if you ignore that modulation, what you see is an exponential fit, which corresponds to an exponential growth of about 3 milliseconds, a growth time of 3 milliseconds. So it's really fast, and this is a log scale. This is about 3 orders of magnitude, which is occurring over this time scale of about 20 milliseconds or so. And the growth is correlated to this radial oscillation. So this is the radial size from the Gross-Pidievsky equation that is very significant in magnitude until you hit the maximum amplitude that the Faraday wave can have, which is limited by the standing wave being no bigger in amplitude than the thickness of the condensate itself. So once the amplitude is 1 in these units, that means that the depth of this standing wave is going through the entire condensate. And so it saturates. So that's the limit of how high this Faraday wave amplitude can grow. So this turns out that if you plot, this is on a log scale, but if you plot the same data on a linear scale and compare it with the theory is these red points, it agrees remarkably well. It's really amazing how good the theory is. And you can see that this part, this initial growth, is exactly what's happening over here, just the last part. So we're not able to get enough dynamic range in the detection of density to be able to see this growth. But what we see in the linear scale is this exponential growth up to its peak, and then the oscillations set in the axial direction, and that suppresses the growth of the Faraday wave by the density. So the point is that we understand these Faraday waves damn well. We really understand what's going on in this system. We understand the dynamics. We understand how they're seated. We understand the frequency dependence. We understand the interaction dependence. The theory from Nicolin is right on. There have been other theories prior to that that haven't been so good, but his theory is a fully three-dimensional theory, which turns out to be very, very important. So we understand Faraday waves well, so to some degree that's satisfying, and to other people that's boring. If you understand something too well, then you're not looking hard enough. So we found some things that we don't understand so well. So for those of you who are more interested in things we don't understand, this is probably a better fit. So we asked what happened with Vanderlei one time during one of Vanderlei's visits. What would happen if we modulated really hard? And I think Kilvia, you might have been there as well, and at one of those points. We modulated the scattering length really hard, so the modulation depth was much bigger than we had for this previous experiment. And we went far from resonance. So we were far from the radial trap frequency, far from the axial trap frequency. and we looked at what would happen, and this is what we saw. So the different strips of data correspond to different hold times going from 50 milliseconds to 4 seconds. So a remarkably persistent pattern developed. The modulation time was 250 milliseconds. Remember before that we were modulating for like 5 milliseconds. So here we're modulating for about 250. And we're modulating very strong. So the average scattering length is about the same, about 5 Bohr, but the amplitude of oscillation was so big that it became nonlinear in the magnetic field mapping to scattering length. The scattering length went from about 15 Bohr on the positive side to about -1 Bohr on the negative side. And again, the axial frequency is about 8 hertz. The radial frequency is about 250 hertz in this experiment, and the modulation frequency was 70 hertz. Remember, in the Faraday wave experiment, everything was bigger than about 200 hertz. That was as far down in signal that we could go. So here we're at 70 hertz. We're modulating the heck out of it. We're really beating up on this condensate really hard for a really long period of time. And what we found was data that was characterized by an extreme and random fragmentation. So these blobs are of all various scale and length. And they appeared to be a result from theory that we did, I'll show subsequently. They seem to be coherent blobs. So these blobs were of very, very different sizes. So you can see, if you look in here, you can see things that are small, things that are bigger, and the separation between them is also randomly distributed. So this looks a lot like what people call granulation. You know, if you take a piece of glass and you break a piece of glass and it breaks into fragments, those fragments are all of varying sizes and various, the glass spreads out in different randomly distributed intervals between them. So it's very similar to the granulation of a piece of broken glass or a rock that you might, smash and break into a bunch of smaller rocks. So this GP simulation that we did before that worked so well for the Faraday waves really utterly fails to describe this granulation. So this is the GP simulation where you see again a very regular pattern which is reminiscent of the Faraday waves. So the GP simulation is not capturing at all what's going on over here. So this is some examples of data. These are single-shot experimental data for various modulation frequencies. So starting with 0 on top, going to 20, 60, and 80 hertz. For 3 different random examples of experiments that we did. So this is the Thomas Fermi distribution of the initial cloud, the initial BEC. After we modulate it for 20 hertz, it develops kind of an odd shape and a little bit of modulation, a little bit of noise on top. But when you go to 60, that becomes very pronounced. So at 60 hertz, there's some very strong modulation of the density profile. And at 80 hertz, it's perhaps even bigger than that. And that modulation is really what characterizes this great depth of modulation, which really characterizes this granulation from what we were doing previously. So this is the density. It's calculated by our collaborators. In fact, one of Vanderlei's postdocs, Mario Satsos, and one of his collaborators, Axel Loda, used something called the multi-configurational time-dependent Hartree method. And they've got a very long acronym for it that I can't even remember. The acronym's too long, so that's when you know you're in trouble. But it was described by Sederbaum in Heidelberg in the chemistry department there. And this paper by Ophir Alan is a very illuminating paper on how this method works, but it goes beyond the mean field. So it uses multi-orbitals like a Hartree-Fock type method, going beyond a mean field using, in their case, 2 natural orbitals. And with this method, they're able to do single shot simulations. And so this shots 1 and 2, this shows shot noise. And as you go up in frequency, you can see that very suddenly, between 20 hertz and 60 hertz, there's a very strong modulation of the density, which appears at the higher frequency. And at 80 hertz, it's very clear as well. So we tried to characterize the observations that we made, first by developing a contrast function, where we took this one-dimensional line density and subtracted from it the Thomas Fermi fit, and that gives us something when normalized to the Thomas Fermi distribution. That gave us something, a contrast function, that kind of characterized, I guess, the depth of the modulation in density. And you can see right at some threshold velocity, the calculation, which is in purple, suddenly jumps up at a frequency which is very close. This is a frequency scale from 0 to 100 hertz. It's very close to what we see experimentally, maybe shifted by just a little bit. And this is, for those of you who are theoretically inclined, these showing some eigenvalues of the first and second order density matrix, which are help characterize when the system is described by a mean field, those second order reduced density matrix coefficient should be small, should be 0. And so at this point, it seems to be the condensate becomes fragmented in that it's not well described by a single macroscopically occupied density matrix element. And that seems to also carry over. If you look at the density, this is again the modulation, this is versus time over here. And at low frequencies below, say, about 20, low frequencies below about 40 hertz, at 20 hertz, we see a modulation of the density. But at 80 hertz, it's very, very, it's much stronger at the higher frequencies. These are the first order correlation functions, and beyond some certain point, those first order correlation functions begin to die. And if you look at the natural orbital occupations at low frequencies at 20 hertz, there is no occupation in the next orbital. And as you go to 80 hertz, all of a sudden this growth is, this other orbital starts to become very significant. So this is an indication that this is a breakdown of the mean field theory, which is occurring over here at higher frequencies of modulation. So that's very consistent with what we see experimentally. And so let me just conclude with that. We've modulated the interactions in several scenarios. We modulated to excite a normal mode of the system, in this case a quadrupolar mode. We used generated at higher frequencies a pattern that's related to something called modulational instability, which can be affected by, in our case, a driven resonance produces Faraday waves, or something in Chicago, which I'll show in the next graph, Cheng-Chin's group, what he calls Bose fireworks. Or you can also quench the interactions rather than sinusoidally modulate them. And we see soliton trains, for example. Other people have seen quantum droplets, which are bound Bose condensates that are actually self-stable in 3 dimensions without a trap. So these are a few pictures of those experiments. These are experiments done in Stuttgart, Innsbruck, Barcelona, and Florence on these self-bound objects. The 2 images that I've shown here, these patterns are in 2 dimensions, is from a ferrofluid dipolar interactions in Tillman-Fau's group in Stuttgart, as are these as well. And these are the Bose fireworks that Cheng-Chin is seeing in Chicago, where he's also using a Feshbach resonance in cesium, in his case, to modulate the scattering length. And in a two-dimensional system, at certain frequencies, they're able to cause an emission of a jet, a forward and backward emission of a jet of atoms that is apparently due to Bose stimulation, like a laser, the matter wave, essentially a matter wave laser. So let me finish up there. So let me acknowledge the people who did the work. There's Jason Wynn, the research scientist in my group, and Henry Luo, the graduate student. And then Gustavo's group, and particularly Vanderlei's group, particularly the theorists Mario Satsos and Axel Loda, and also the experimental work of Gustavo and Vanderlei, who came to our lab over many occasions over the last few years, and been greatly appreciated and led directly to this work. So thank you.
Questions?
Randy, the Faraday experiment with liquid, water or whatever, the waves are superficial, right? We actually don't have that pattern propagating to the bulk of the fluid.
So in the original Faraday experiment, the waves are on the surface.
Yeah.
So it's just a surface wave.
Okay. So suppose that we can excite this in a 3D fluid,
Yeah,
in a 3D BC.
yeah.
What do you think will happen?
Yeah.
We're going to create a surface waves, and then we're going to keep pumping energy.
Yeah.
You think this will break in grains in 3D?
Yeah, so this system is not a 1D system that we've been looking at. It really is 3D. It really fits the Thomas Fermi distribution very well in all three dimensions. It's just very highly elongated. The Faraday waves are always surface waves. And what I found, what I showed earlier was when the modulation is increased to such an extent, the modulation strength and duration, that the standing wave is as deep as the condensate is thick, then it breaks down and the growth stops at that point. So it really, you're not, since it is a surface wave, you're not going to get it through a all the way through a three-dimensional system.
No, but in the surface I can produce on the surface I can produce a stationary wave, right? It's like a bubble. But my question is, you think that we will evolve to similar things?
You mean at the parametric resonance at twice the megahertz?
Yeah, no, I think if I do the same experiment in a real, in a bulk, I see the waves at the surface, and then you think how this will evolve. Am I going to break in grains?
You mean the grain?
Yeah. The grain, yeah.
Away from the Faraday resonance.
Away from, yeah.
Completely different frequency.
Yeah.
So, eventually you have to keep the heck out of it because it's absorbing a lot of energy. So one of the calculations that Marios made that I didn't show, Marios and Axel, was that the average energy of the system is increasing as you modulate, but not by very much. So we're talking, tens of percent increase in energy. But I think that if you kept going, if you kept modulating it, you would eventually make a classical gas. You'd eventually destroy the condensate, and you would lose all coherence in the system. It's not an experiment that we've done. But maybe
I know, but this is something that can be.
You showed the multi-configuration results. Can you measure the correlation function to corroborate that multi-configuration really is working as the experiments?
I didn't show that because it's a very, very theoretical thing to explain. But there is, in our paper, there is a plot of the correlation function. Well, what I did show the second order density correlation. So let me show that again. Maybe this is what you mean. That first order spatial correlation. So that shows the correlation as a function of z, which is the separation between 2 points along the condensate axis versus modulation and hold time.
It's experimental. The right side.
No. This is all theory. Yeah. So the difference is on the left side, it's a modulation frequency is below this threshold that we observed, and on the right-hand side, it's above the threshold. So the threshold seems to be somewhere around 40 to 60 hertz. That if the frequency is not high enough, then we don't see this effect. So the frequency, the phenomena turns on very suddenly with frequency going above this critical frequency. Let me show you again. So here. So this is the top graph is this density contrast function, and it's essentially, 0 until you get to this threshold frequency of around 40 hertz. And so that the light blue on the top is experimental and the purple is theory. And on the bottom are the eigenvalues of the reduced density matrix for the first and second order. And you could see that there is also shown evident in that when you get above about 40 hertz, that suddenly those other orbitals become important. You start losing the coherence.
You just said that the system was really three-dimensional.
Yeah.
And what about the calculations? Are they in one-dimensional?
Yeah, they're in 1D. So okay. Yeah, so the calculations are in 1D, and the experiment's actually in 3. And so there is some question about the validity of the theory that we haven't fully answered. And I believe that we haven't fully answered that. Marios and Axel maybe disagree with me on that, but there's really nothing that happens. The fragmentation doesn't happen radially, so it looks like a one-dimensional system. So if you look at the density profiles, the two-dimensional ones, you don't see anything radially. And part of that is that the radial size is getting to be close to our optical resolution. But it doesn't appear that there are anything special happening in the radial coordinate. But theory is not good enough to be able to do 3D. It's very time consuming.
Further questions? Wanderlei has one, right?
Randy, this is very speculative because we have a superposition of two many-body states. You think the time evolution of this is interesting? I mean, does anybody know the time evolution of a superposition of two many-body states?
No.
Because here we could see the time evolution. And
yeah. So,
which is something.
Yeah, exactly. So this is a start. Obviously on this subject, and there are many interesting things that we can do. It would be interesting to do a time of flight expansion and looking at the density, like the experiments you do. Look at how the density depends on how k depends on the momentum. Yeah.
Yeah, maybe just a small comment on this most recent statement. This is two orbitals, and all the bosons are distributed onto these two orbitals in the many-body wave function, which means not two many-body states, but n over n minus 2, which is scaling with n many-body states. So it's how you distribute the bosons onto the orbitals, which is the allowed many-body configurations.
It should have a time evolution.
Of course, it will have a very complex time evolution.
Will you record, will you have oscillation?
I'm sorry?
Then we have an
Sure. Yeah, and the just a second comment, that the restriction to two orbitals is of course a restriction if you think about convergence and so forth, but as it stands, it gives qualitatively the right features, yeah.
Chris?
It's not such a long acronym, is it? MCTDHB? It's not such a long acronym. MCTDHB, isn't it?
I can't remember it. There's too many letters. It exceeds my buffer size.
No, they can be long. This we discussed during lunch break. Okay, is there more questions? Okay, if not, let's thank Randy again for this nice talk.